PhD student at the University of Victoria. I just started this past year, and I've also been on the tsunami hazards team at the Washington Geological Survey for about the past 6 years or so. But today I'm going to be talking about implementing the Watada correction and Kajiura filter in GeoClaw. And I'm going to start with the Kajiura filter. And this is a depth-dependent spectral transfer function that transforms coseismic seafloor deformation into an initial sea surface elevation. And more specifically, it takes the deformation of the seafloor and converts it into a physically consistent and smooth surface displacement, which then can be used to initialize tsunami models. And so this transformation is performed in the spectral domain where each wave number component is scaled by a factor that depends on the water depth. And on the equation that I'm showing here, the relationship is governed by this hyperbolic cosine term where wave number k represents the spatial scale of the deformation and h naught is the representative initial water depth. And this formulation provides a simple way to account for the finite depth of the ocean when translating that seafloor motion into the sea surface elevation. So how does the filter actually behave? The key concept, which I want to show here in the upper transfer function plot, is that the long wavelengths pass through unchanged, while the short wavelengths are increasingly being attenuated. And this behavior is essentially equivalent to sort of a depth-dependent low-pass filter. So, for example, when the transfer function is close to 1, the seafloor deformation is transmitted almost directly to the surface. So the filter has very little effect at those scales. And then now we transition to the lower plot on this slide. I quantified this effect for a real earthquake example. For my PhD research, I've been studying the 2021 magnitude 8.2 Chignik, Alaska earthquake. And in this plot, I'm using a 200-meter water depth as a baseline for comparison. And we can see that the representative water depth, as the representative water depth increases, the filter attenuates a broader range of wavelengths. So the difference from the baseline also increases. However, for this particular Chignik earthquake example, even at greater water depths, the overall difference remains quite small because the deformation field is already dominated by long wavelengths. So in scenarios with perhaps more short wavelength structure, the filtering could produce larger differences than what I'm being shown here. So now that we've sort of covered the Kajiura filter and how it behaves in theory, the next step that I'm going to be talking about is how to apply it to generate initial conditions for tsunami modeling in GeoClaw. And this diagram outlines my general workflow. I first started from a dtopo file and I defined a representative water depth, and then I applied the filter in the Fourier domain or its wavelength components to attain the filter sea surface elevation. And then I write the results back into a dtopo file with the same structure. I then performed a set of diagnostics just to verify the filtering behavior before using it in GeoClaw. And I also wanted to mention that I did this kind of workflow with two different testing outputs. I wrote both to dtopo and also QInit, and I found that the dtopo approach was much more stable to work with, while the QInit introduced this odd basin-wide mean sea level offset that's seen on later times. And I'm showing this waveform here in the bottom right of the screen that you can kind of see how the blue line, which is the Kajiura with the Q in it, the mean sea level kind of drops below what it should be. And I'm not entirely sure why this occurs, but my current thinking is that it's because QNet is directly prescribing the initial surface, and it could be more sensitive to small mean offsets and edge effects, which may be causing this sort of adjustment. But I'd be really interested if anyone has seen this before or something similar when using QNet, and maybe we could chat more about this afterwards in a breakout or offline. So let me know about that if this is something that has been an issue before. But back to the Chignik example, so using the published slip model from Liu et al. 2023 for this Chignik earthquake, we can directly compare the original and filter deformation fields to assess any changes in both amplitude and structure. And the key result is that the filtered field closely resembles the original at large scales, meaning the overall source geometry is being preserved. And we can see that the primary effect of the filter is a subtle smoothing of small scale features and sharp gradients, which reflects the attenuation of the short wavelengths. And even in this strong filtering case where I use a 4 kilometer as my representative water depth, the difference fault highlights where the filter is acting, and these changes are pretty small. And building on that previous slide, we can also now look at how sensitive the filter deformation is to the choice of water depth for this particular example. In my center plot here, I'm using a shallow depth of 200 meters, which is more aligned with the Chibnik, Alaska earthquake region. The filter with this depth, has almost no effect, and the deformation is nearly identical to the original. And this contrasts with my choice of using 4,000 meters, where we see a slightly stronger smoothing of the small scale features. But still, when comparing these two end members, the overall deformation pattern remains very similar. So the difference map now that is shown on the right side of this slide um, also highlights where the depth-dependent filtering matters the most. But these changes are again really small for this example. So for this event, the Kajiura filter is not highly sensitive to reasonable choices of water depth that match the geographic location for this source region. So now an important question for the 2021 Chignik event is, does the Kajiura filter actually impact the tsunami signal? On the left is a near field dark station, and on the right is a far field dark station. And across both cases, the waveform from the original deformation and the filtered versions, while using both the shallow and deep representative water depths, show that the waveforms are almost indistinguishable. In the near field, you can see some very slight differences when using the deeper representative water depth of 4,000 meters, which is consistent with stronger attenuation of those short wavelengths. But even there, these differences are quite small. And the time the wave reaches the far field station, they essentially disappear altogether. So for this particular case, this magnitude 8.2 Chignik example, the implementation of Kajiura filtering has very minimal impact on the resulting tsunami. However, I suspect this outcome is likely tied to the specific structure of the Chignik source and perhaps other deformation fields with sharper and more discontinuous slip, such as some of the Cascadia models we've been working with at Washington State, like L1. The filtering could play a much larger role. I have not tested or explored applying the Kajiura filter to the L1 model at this time, but I hope that this is something I can eventually do, and I'm interested in testing this for our other source models in different locations. So, in addition to the Kajiura filtering, I'm now going to transition into my other topic and introduce the Watada phase correction, which accounts for dispersive effects during tsunami propagation that are not captured by the shallow water wave equations using GeoClaw. So while GeoClaw does have a boost and S version that includes dispersion, like we heard a lot about yesterday and earlier today, the Watada correction can provide a simple way to approximate these effects directly at tide gauge locations. And I think it would be interesting to compare these two approaches more systematically in the future. And I hope uh, someday I can get some of this done as well, and maybe talk with other collaborators here about this. So how does the Watada correction actually work? This approach operates in the Fourier domain where the tsunami signal is represented in terms of wavelengths, and the phase of each component is adjusted depending on its wavelength, which effectively changes the wave speed and introduces dispersion into the signal. The result is a small delay in arrival time and a there's a subtle phase shift in the waveform, and these effects become more pronounced as the propagation distance increases. And we see this in the example figure here on the right, where the waveform spreads out and becomes more oscillatory as it propagates. So for implementation into GeoClaw, I followed the methodology from Watada et al. 2014 and used the Semi 1D code as reference, which is also publicly available on GitHub. The correction is applied as a post-processing step to the GeoClaw gauge outputs using a single Python script. And the key input is the source to gauge distance, which I compute using a great circle distance between the source and each gauge location with Haversine equations. And for each gauge, the model time series is extracted, and then the correction is then applied based on that calculated propagation distance. So also importantly, this approach does not require modifying any of the GeoClaw solvers itself, and that makes this a relatively simple and flexible way to incorporate simplified dispersive effects into GeoClaw. And to further validate my implementation, I applied my Watada correction script to a raw high C gauge that was shared with me by another modeler, which did not include any dispersion. And I then compared this result to a reference solution for the same gauge that already included the Watada correction generated by the other modeler. And as you can see on this plot, there's very strong agreement between the two, which confirms that the correction is being applied correctly and reproduces results from an independent model. And finally, to illustrate how the correction behaves, I varied the source to gauge distance L while keeping everything else the same for the same gauge output from a geoclaw simulation. This again is using one of my Chignik earthquake examples that I've been studying. And here the lower plot uses the calculated source to gauge distance for this station, while the upper plot shows an artificially larger difference for comparison. And we can see what we see here is that increasing the propagation distance introduces a larger delay and a more noticeable phase shift in the waveform. And this is consistent with the dispersive tsunami physics, where longer travel times allow these effects to accumulate. And this result reinforces that the Watada correction is capturing the expected physical behavior of tsunami propagation. And to wrap up and summarize my two topics for this talk, the Kajiura filtering had minimal impact for this Chignik case that I've been working with, while the Watada correction introduces physically meaningful dispersive effects into GeoClaw. And this implementation again is implemented as a simple post-processing script and produces results consistent with independent models like High-C. And then lastly, I just wanted to include the links to the code and methods here for anyone interested in applying these approaches. And I'd also be happy to share these scripts as well. Thank you.